Yeah, yeah. I mean, so we're all gonna plug in our own.
Yeah, assuming it was.
Yeah. So I guess.
I think you can definitely, you know, you can train in your Mac.
I'm gonna try mine out after yours. You're in Potsdam, are you?
No, I'm at Hanover.
Oh, I see. Oh, okay. So the Albert Einstein Institute was in Potsdam for some reason. Oh, there's two of them. I remember.
How about we doing our slides on our own laptops?
I think I don't know. I prefer always my own laptop because
Yeah, I
I know
can
it
do
works.
that too, because some other session people have been having things like this.
Yeah, I meant I think like I mean the Mac is most of the time there. And did you read my proposal?
Just afternoon, before we leave. What time are you leaving?
I'm leaving at like 11 o'clock or something like that. Really?
Oh, okay. So
No, don't worry about it.
no, because if we get a chance to talk about it while we are here,
Yeah,
in
would be
person,
fun.
that's
Yeah,
always good.
yeah. I mean, yeah. I think I told you yesterday what sort of to do. What I think of doing.
Need a different dongle, of course.
Everyone has their own dongle.
No, this would have worked for me. I don't know how to switch between these. What does it detect automatically?
Did you check your?
That's all.
Okay.
You guys are talking, I'm just warning you the microphone is on. Goes green, then you're just bring. Good.
Could we ask everyone to take their seats, please? We're going to be starting in 1 minute.
Oh, it's got a click in it. Oh.
So this computer that you're presenting as internet access, we are not.
Well, you have to bring her on. Bring her on.
Have to bring my own.
Yeah. I think that's the best move.
Okay.
That's the most
Because it's
reliable
on Google
move.
Slides.
I see. Yes, you could just use the you could just use the person before you, which I guess is on.
Yeah, but I think it was just bring your own internet.
Oh, okay. We might actually wait a second. We're just gonna do it right now. We might just put you on. Can he use your computer with a browser? He probably wants Google Chrome.
Yeah, exactly.
Company. He has to use the company. Infrastructure.
Turns out everyone in Google X is using the
Microsoft. Oh yeah, yeah, I have Brave. I know some of the devs on Brave actually. But no, we're good. We'll just use this. Then we have no transition there.
All right, I think you should. All right, we're about to get started.
Hello. Okay, people. Enough interacting, learning things from each other. You're done. Insightful chatter. It's over. Okay, people. So I'll give you technically you have 16 minutes. So at 15, I'll tell you you've got 1 minute to wrap up. If I remember to turn on my timer. Otherwise, you can just go for as long as you like. Great. Oh, good. Okay, good. We're ready to start. Our first speaker is Colin Capano, who is at the Albert Einstein Institute. Take it away.
Thank you. Colin, I'm a postdoc at the AI in Hanover, Germany, and today I'll be talking about using Bayesian inference to search for subthreshold GM. It's my fault. Now I have the voice of God. Yeah. Okay, so what is the motivation for searching for these things? So we all know about GW 170817. It was an extremely loud event. On this plot here, I have false alarm rate, and on the x-axis, I have essentially a ranking statistic that's like SNR. GW 170817 was the loudest event that we detected in 01, 02, perhaps 03. I'm not sure. I'm no longer in LIGO, so I'm not privy to that anymore. And you can see it sticks out way, way, way above anything else that we have. This is a set of triggers or candidate events that we have from the gravitational wave detector from the first observing run. And you can see all of these have very large false alarm rates. And there's thousands of triggers here, and the vast majority of these are noise. However, based on the rate estimates from GW 170817, you might expect that there could be one, maybe even two binary neutron stars buried somewhere in that noise. And so what we want to try and do is see if we can extract one of those by combining the data with the gravitational wave data with the EM data. And specifically, when I say EM, we're going to be focusing on GRBs. And what we did here is do a coincident search between the LIGO detectors and Fermi GBM. We're not the first people to do this. There's been plenty of searches in the past by the LSE And I list 2 papers here that were analyzed on O1 data. Neither of these papers found anything, which wasn't too surprising. This first one was a GRB triggered search, and the fact that it didn't detect anything wasn't surprising because most GRBs are just very far away. The second paper here was a search that tried to look for more subthreshold GRBs, more like what the 1708-17 was like. But again, this did not find anything. Part of that was it just did a time coincidence search with what they said in eyes wide open, which meant that they were looking for, they were allowing for the possibility for binary black holes, for instance, to produce GRBs. Here, though, we're going to do a time and location coherent search, and we're just going to target binary neutron stars because, let's be honest, that's what produces GRBs. Sorry. The short ones, fair enough. Not black holes, though. So for the gravitational wave candidates, we used a collection of candidates from this 1OGC catalog that we had created earlier this year. This was basically a reanalysis of the O1 data using a templated search. Basically, we lay down a grid of templates over covering binary neutron stars, neutron star black holes, and binary black holes. And then we filter those with the data to produce a list of candidate events. This search on its own didn't turn up anything surprising. We basically refound the events that were already published by the LSC. For this, though, what we did is from this list of candidates, we down-selected just the binary neutron star range. So we just looked at the lower mass end of this thing, and this reduced the number of candidates we had to about 3,400. We also included some single detector time. This was, these guys were from times when both detectors were on. And because we are throwing in the GRB detector, we are also able to include times when just Hanford or Livingston are on. Oops. For the GRB candidates, we used all short GRBs, short hard GRBs produced by Swift BAT and Fermi GBM in the O1 time range. We also used some the subthreshold events reported by Fermi GBM on this website here. We also, because we actually even want to dig even further down into the noise, we actually produced our own candidates. We ended up just doing a very simplified thing. So on the Fermi GBM, there's 12 detectors, and we essentially just summed the photon counts over all those detectors. It's not optimal, and I'm going to come back to this in a few minutes, but it was something that we could do to get candidates. For these ones, I should also mention, this is going to come up later, we didn't really have a sky location for these because we didn't really know how the Fermi GBM response function works. The only thing we could do is account for the location of the Earth. So how do we do the actual joint thing? Well, we looked for temporal and spatial coincidence. In time, we just insisted that the GRB must be within 0 to 3.4 seconds after the gravitational wave candidate. And this window was chosen based on GW 1708-17 was 1.7 seconds after the GRB was 1.7 seconds after the gravitational wave trigger. So we just doubled that time. For the spatial, basically you take the posterior. You have a source location posterior for the gravitational wave channel, and also from the telescope, in this case Fermi. And basically, you just multiply these two posteriors together and you integrate to get what we call a spatial Bayes factor. And this demonstrates that here. So, if you have the posterior from one of the detectors, the other, you multiply these two together, and then you integrate. And the more they overlap, the larger the number, and the less they overlap, the smaller the number. Richard basically discussed Bayesian inference in pretty good detail before, so I don't think I need to go into this too much, but basically what we mean when we say a posterior is you have some probability of observing some set of parameters, assuming you have some data and some signal. You rearrange this to write it as likelihood times a prior divided by the evidence. And then this is a multi-dimensional thing. If you just care about 2 dimensions, say the right ascension and the declination for the sky posterior, then you can just integrate this multi-dimensional thing out to get your sky posterior. This is an illustration of this in action. So this is on the, here I've got two masses from an event, and the z-axis is the posterior probability. Here, this is the right ascension and declination from a different event, and each one of these orange points represents a MCMC chain. So you learn what these posteriors are by stochastically sampling it. So in this case, we've laid down a whole bunch of chains, and then you just run these things, let them run forward, and eventually you end up getting the posterior. Now, for this analysis, we used PyCBC Inference, which is a module in the PyCBC software suite, which we use to do this search. Excuse me. And PyCBC Inference is what we use to do this Bayesian inference. Now, as Richard had mentioned earlier, waveform generation is extremely slow, and we have 3,400 candidates that we want to try and produce sky posteriors for. So what we did was we fixed the intrinsic parameters, the mass and the spins, and that allows us to, and we fixed those to the values of the mass and spins we had from the search. And this allows us to basically produce sky posteriors very quickly. It's very similar to what's done with the online analyses that the LSC does. So we fix the mass and spin parameters, and we vary the RA, deck, distance, inclination, and polarization in time to produce sky posterior. And then we calculate the spatial Bayes factor between our posteriors and the GRB sky maps. And then we come up with a ranking statistic, which is basically the SNR from the gravitational wave side plus 2 times the log of the spatial Bayes factor. And then to get a significance for events, we basically repeat this analysis by time shifting the GRB data with respect to the LIGO data 10 to the 4th times, repeat the analysis, and get a p-value. So these are the results from our search. The y-axis here is the cumulative number of events per the observing time. The x-axis here is our ranking statistic. There's a few different lines here. I just want you to point out the blue one here, and this is the expected back rate of these things from noise from our time slide analysis. And the 2 stars here are what we got from our actual analysis. And you can see that there's one event here that actually is fairly significant. It had a p-value, a 2 sigma p-value, which when you fold in some information from the astrophysics gives you about a 1 in 4 chance of being astrophysical, so 25%. This on here is a plot of what the SNR from the gravitational wave side here. So this is the Hanford detector, Livingston detector. Y-axis is SNR, x-axis is time. And you can see there's a little spike here. The SNR in each detector was around 6. This is our counts from Fermi GBM, and you can see it shows up right here. Now, recall that I said we created our own Fermi candidates. This is one of those. So this was arrived at by just summing up the GBM counts. And we ended up with a count of about 5.7. For reference, GW 170817 was 10.5, and the quietest GRB that has been published has a count of 7.2, so this was quite a bit more quiet. This is what the sky location looked like for it. So the blue here is our sky map that we get, and as I said earlier, we weren't able to produce a sky map from the Fermi GBM. All we could say is, well, it can't be where the Earth is, and that's what this gray shaded region is. And because this is rather crude, the spatial Bayes factor we got for this was only 0.8. Now, I said it only has a 25% chance of being real, but let's assume for a second it is real. We then went and did PE on the full thing to get estimates of the parameters, assuming it is real. So this is chirp mass. Here we've got mass ratio, the effective spin, inclination, and distance. And basically, because this thing is so quiet, the only thing we can really get a measurement of is the chirp mass and the distance. Now, using that distance measure, though, we can, again, if you assume that it's real, we can constrain the speed of gravity. This is the value we get from that. And these bounds are actually better than the GW 170817 bounds, which isn't too surprising because this is further away. Further away it is, the tighter constraint you have. And for that reason, and another motivating factor for doing these sub-threshold searches is if you can convince yourself that these things are real, your best limits are always going to come from these because these guys are always going to be the furthest ones away. So, was this event real? Well, I don't know. It's a 1 in 4 chance. If you were told an airplane had a 25% chance of crashing, you wouldn't get on that plane. If you're a political candidate, though, and only had a 25% chance of winning, you would think you're not going to win, unless you're Donald Trump, apparently. I keep on forgetting I don't have a control here. Now, I said we didn't really have a sky map for this thing, and the big reason for that is the code to be able to produce those sky maps wasn't readily available from Fermi GBM. Now, the odds that this thing are real might increase if we actually did have a full GBM sky map. Who knows? It probably, though, for the most part, will always remain at that. But in the last couple minutes, so I just want to say how we might be able to improve this search going forward. So even better than just having a sky map from Fermi or any other EM telescope, if you had a likelihood function that was readily available, say in a Python module, then you could do, I think, a much better search here. So recall our equation for the spatial Bayes factor. You had that posterior on the sky location from each of the two detectors multiplied to each other, and this has been marginalized. All the extra parameters have been marginalized out when you produce this. But if you massage this equation a bit and you write it in terms of the likelihoods, you could write it out in terms of the GW likelihood times the EM likelihood with all of the parameters written out. And the nice thing if you did it this way is if you had if you want to do something more sophisticated, like look at coupling some of the other GW and EM parameters together, you might be able to get a better Bayes factor. So for instance, you might imagine if you had a model for how the luminosity of the GRB falls off with inclination. Well, you have an inclination from the GW, you could combine that together with the GRB data. Or if you're using like LSST, and you had a galaxy catalog, you might imagine jumping over the galaxies instead of the sky parameters directly. And to be able to do this, the infrastructure to be able to do this is, from our side, is basically there. So this is a call graph for PyCBC inference. There's a lot going on here. I'm not going to get into this. The main thing I wanted to highlight is this is all in Python, and we already use external modules in this. For instance, our waveform generation on the GW side uses LAO simulation, which is external to PyCBC. Our stochastic samplers, we use external ones like MC, MCPT, or Multinest. It would be very trivial that if there was some Python module with that gave you, if you gave it, you could give it, say, a sky location, 1 minute, no problem, for some external EM telescope like a Fermi GBM, and it gave you back the likelihood, it would be very trivial to fold this into this entire infrastructure. Basically, adding support for this on our side would take essentially 10 lines of code. So the main challenge here is, is this possible on the EM side of things? And that's actually how I want to end, and partly why I came here. I was hoping to spur that question. So to summarize, we've done a sub-threshold search. We found a candidate, 1 in 4 chance of being real. But there is, I think, a lot of opportunity to improve this sort of thing going forward. So thank you.
Good, thank you. Next we have Daniel George, who's here from Google X. Mic is on. That's good. Good. I'll give you a warning when you have 1 minute. 16 minutes.
All right then. So today I'll be talking about my PhD thesis. I graduated recently. It was on deep learning methods for gravitational wave and multi-messenger astrophysics. So let's get started. So what are some things that you need for like an ideal pipeline to enable like real-time analysis of data for multi-messenger astronomy? So you need something that's really fast that can analyze gravitational wave data in real time or low latency. You need something that can be scalable to like all the parameters of a source without taking too much computational resources. It should be able to detect many different types of sources, even though you don't really have many templates for these types of sources. You also want it to be resilient to non-Gaussian characteristics of the noise. So you want something that's optimized for the real noise characteristics, not just assuming that it's a Gaussian white noise or something. It should also be able to classify known types of sources and, as well as glitches in the data in real time. And ideally, you also want it to be able to detect anomalies where you don't know what the signal looks like, so that you can do like unsupervised clustering or classification. And you also want a rapid sky localization that is very accurate, so that you can immediately follow up the sources. So the objective of my thesis was to try to develop a new method that can tackle many of these challenges. So if you look at just the raw LIGO data, it's very noisy. So if you look at 4 of these examples, you cannot see a signal in any of them, even if you look at the time series or the time frequency maps. So it's a really hard problem because the signals are very weak. It was the first and the last one that had this like very weak signal with a low SNR, and our goal is to detect these really accurately and very fast. So what do people do right now? Something on match filtering. You have a huge template bank, and you try to compute the overlap as the data is coming in. You try to compute the brute force overlap against hundreds of thousands of different templates that you get from simulation or other semi-analytic methods. So this is the optimal method, assuming you have the same exact template bank as the signal in your data, which is not always the case because templates banks are sparse. And it's also not the optimal method for non-Gaussian noise, which is the case with LIGO. It's not exactly white noise. And since the template bank is sparse, the initial estimates of the parameters would be off because the exact same parameters are not in your bank. So these are some limitations, and I proposed to apply deep learning using artificial neural networks to improve or complement match filtering. And this is the case if you look at computer vision or for audio, like speech processing. People have tried similar methods before, and deep learning is the state-of-the-art method. So you don't use a billion templates of cats and dogs and compute the overlap to actually detect if something is a cat or a dog in a photograph, or the same with audio. So this was the reason why we proposed to try the same thing for gravitational waves. So these are the 2 publications that came out last year. The first one, we proposed to apply deep neural nets for classifying gravitational waves in the data, basically detection as well as parameter estimation. We showed results and comparisons with match filtering with simulated data, white noise, Gaussian noise. And in the second paper, we applied the same technique and showed that it works with real LIGO data. And for the first time, we showed that you can actually detect real gravitational wave signals using the deep learning method. So what is deep learning? It's a machine learning technique that's really popular these days. You apply very deep neural networks. So we've already talked about this before. So it's the current state-of-the-art method for all kinds of things: computer vision, speech, audio, self-driving cars, even playing games such as Go, where AlphaGo is like the current state-of-the-art method that beat all the world champions at Go. So we adapted this technique for detecting gravitational waves and for estimating initial parameters for these waves. And the main advantages of applying deep learning is obviously you don't need handcrafted feature extraction before. You can just feed the raw data into the pipeline, and it can do everything end to end. So this was the structure of the convolutional neural network that we applied for classifying gravitational waves and estimating the parameters. So you can see it's a very simple convolutional network. It's inspired by what people use for things like handwriting classification. So you have 3 convolution layers and 2 fully connected dense layers, and you assume the input is a 1/n image. So it's a raw time series data. It's a 1/n image. You feed it directly into the neural network, and you can train it using signal injection. So now you know the labels. You know where you're injecting the signals, and you know what the parameters of the signal are. So you use that as training data, and then you test on real data and see if it works. And there are some tricks that we found for improving the accuracy. It was you use a mix of real noise and simulated noise while training, so that way you get a lot of data. You can artificially enhance your training data size by combining the same signals with different noise. And then you start by training the neural nets on an easy problem where the signal to noise ratio is very high, so that and then you slowly decrease the signal to noise ratio so that it's called curricular learning, where you start with an easy problem and then you make it harder gradually. And you have two neural networks, and we have the same shared weights between them. The first one tells you yes or no, whether there is a signal in the noise, and the second one tells you these are the masses of the black hole, so on. And so we use real data. You put real noise into the training process to make sure that it's resilient to the characteristics of the real noise. Like, you can see all these glitches in the data. So the neural network is actually seeing this and learning from it. So it's developing something that is optimal for the kind of noise that it sees. So this is a comparison with match filtering, and you see for the same kind of signals in your template bank, it's able to closely reproduce the sensitivity of match filtering with the same template bank. And I'll show you later what happens when there are things beyond your template bank where it would perform better. And the main advantage is it's really fast. So all the computation goes into the training process. So you can use like a supercomputer and a lot of GPUs to do the one-time training thing. But once that is done, the inference can be carried out in it takes in like milliseconds for analyzing 1 second of data. Especially with the GPU, you can get a huge speed up because GPUs are now dedicated for deep learning. It has special cores like tensor cores for doing deep neural network computations in real time. So you can actually, even when you process like a lot of data, like in batches, you can analyze like a year's worth of data in like a few hours or like minutes. Now, so that was classification detection. Now, for like estimating the masses of the black hole signals, you can see that the deep learning method is actually more accurate because it can interpolate between points in the template bank. So even though the template bank was sparse, the neural network can interpolate and predict parameters that were not exactly found in the template bank. So that is an advantage. And of course, the neural network does better than all the traditional machine learning methods because the data is very noisy. So this is something where the convolutional neural network has an advantage for both detecting and estimating the parameters. And also, what is the new physics that we can do? We found that even though we only trained the convolutional networks with non-eccentric, non-spinning binary black hole templates, the neural network is automatically able to detect these eccentric black hole signals that we injected. So we did these simulations, we injected this in the noise, and we found that even though the neural net had never seen signals with these eccentricities, it was able to automatically detect them. So neural networks has the advantage that it can generalize to some extent to things that it hasn't seen before, which is really great. This means we might be able to see signals beyond the template banks that we are using. So here we can just look at a video of showing what actually happens when you're applying the neural network on the data. So this is the first detection, the GW150914. You can see the output of different layers of the neural network as you're sliding the net through the data. And once it reaches the point of the signal, you see all this activity happening in the third layer and forwards. And it says that, right now it says it's not detected, now it's starting to detect it, and it predicts the masses of the thing within the error bars, which is pretty good. All right. And another advantage is that this method is automatically resilient to glitches. So here, like some simulated glitches, all kinds of sinusoidal waves that we simulated and tested the neural net on, and it was able to classify that this is not a signal. And the false alarm rate was on a data set of these glitches was like 1%, whereas if you just do naive match filtering and just look at the SNR output, it produces a very high SNR. So it could be classified as a false alarm. And it also works when the signal is superimposed on a glitch. So now you have the sum of a glitch and a signal, like what happened for the first binary neutron star detection, and the neural network is still able to detect these sources even when it is superimposed on a glitch. So we would not actually miss these events if there was a very loud glitch in coincidence with one of these signals. It is also getting like pretty good estimates of the parameters as well when there is a glitch on top of the signal, which is awesome. So to summarize some of the advantages, it's really fast. It can be trained on basic, you just need to do the training once. So you can actually train it on like millions or billions of templates if you actually just use a supercomputer once. It can find new sources even though they were not in your training data, like eccentric black hole mergers. It's resilient to anomalies in the noise, and it's optimized, kind of optimized for the type of noise that you have to deal with, not assuming that it's Gaussian or white noise. And when you consider interpretability, we don't actually want to replace the entire pipeline and just believe what the neural network says. You can use it as like an initial trigger generator or an initial parameter estimate, and then you can just follow it up later with match filtering or the full PE pipeline. So it can actually be used somewhat in like a hierarchical search, for example, by constraining the template bank that you actually need to search for, which might be an ideal use case. So now I'll also talk about another work that we did for detecting anomalies and glitches and unsupervised clustering of new kinds of sources. So what are glitches? These are these non-Gaussian transient features in LIGO data. It could be produced by the environment or some parts or some instruments in the detectors going wrong. Identifying them is critical to improve the quality of the data, to prevent false alarms, to actually fix the instruments based on how they're behaving. So there's a project called Gravity Spy, which is a citizen science campaign that looks at these time frequency maps of the detectors and then uses human citizen scientists to actually classify them into different labels. So we have like few thousand labeled examples of various glitches that have been found. So why not try to automate this process and learn from the label data we have? So we propose to apply, again, convolutional neural networks, but this time the data is very limited, just a few thousand examples. So we thought, let's try transfer learning, where humans really aren't trained to look for glitches, but we can learn really fast after seeing just a few examples. So the same idea, you use a neural network that's already been trained on millions of images and see if we can actually use the knowledge that the net has and train it to identify glitches by just showing it a few examples. So we tried this with this network called Inception that Google uses now. For example, when you use Google Photos and search for cat and it pulls up all the pictures in your album that has a cat, it's actually using this network called Inception, like version 3 or 4, to actually do that. So we took this network, which has already seen millions of different images with like thousands of different classes of objects, and we fine-tuned it on this data set of glitches from Gravity Spy. And we got the state-of-the-art accuracy at classifying these known labels, like almost 99% accuracy, which was really good. And with many of these classes of glitches, we got perfect accuracy, perfect precision, and recall. So the idea was you take this convolution network, then you chop it off, and then you use the truncated convolution network, and you just keep the weights that it already has. So it already knows how to extract a lot of features. So now you can use this as a really good feature extractor. And another side effect of this is you can use this convolution network that is truncated as a feature extractor where you feed in any image and it outputs some numbers, a few, like 4,000 numbers that is correlated to the features that it sees in the data. So now you can actually use this for doing unsupervised clustering of even new classes of glitches that are anomalous signals that are not labeled. So you don't have any labels, but you can still use this as a good feature extractor for doing unsupervised clustering. So we simulated a synthetic class, which is basically a black hole in reverse. So you can say it's like a reverse chirp, and you find that it's actually forms a new cluster. So you can use clustering algorithms like spectral clustering or k-means or something to actually do automatic anomaly detection and finding new categories of glitches that might show up in the future. So this is pretty promising. Yeah, so basically that is it. Thank you, and most of this work was done at the Gravity group at NCSA. All right, thank you.
while Wolfgang sets up, I'll use his mic to say this is Wolfgang Kurtzendorf, who's currently at NYU and headed to Michigan State.
That's right. Thank you very much. Oh, look, it works. That's always good. Does this work? Yes, I'm loud. Well, thank you very much for giving me the opportunity to chat about emulators, which for a long time thought I was the only one who had this crazy idea, but there's now many people, and it's great to have such an interdisciplinary conference where there's mathematicians and statisticians as well as like physicists from all fields. I'm an astrophysicist, and I'm not doing gravitational waves. I study, let me just do this. I study the lives and afterlives of stars in the sort of EM spectrum, and I think one of the and mainly I focus on supernovae, and I think like one of the cool things and that we can do with supernovae is we can see stars very, very far away. So I mean, for a few weeks to maybe months, like a single star outshines an entire galaxy, and so we can learn a lot about distant stars. But we can also learn a lot, about the inside of stars. We have an evolution which we normally don't have with stars. Like stars are pretty stable over gigayears, megayears to gigayears timescales, and this sort of gives us a way to study these objects. So, to give a brief intro, exploding stars, you sort of take an unexploded star, you somehow explode it. And then you have a theoretical model that sort of shows you nice turbulent burning, deflagration, and detonation. But I mean, as we all know, everything in physics is spherical. We can approximate this easily and very correctly with this thing. So this is a white dwarf that exploded. Essentially, we have nickel 56 decaying in the middle and sort of powering the light curve and the spectra of this explosion. So I said, you can look inside of stars, and the way you can do this is with supernova tomography. And I think this is a really, really cool thing that people have been doing for a long time now. So, because what happens when you have sort of a white dwarf explode, or generally stars explode, you have a so-called, you can approximate it as a photosphere, and you have an opaque sort of inner core. And as this sort of moves out, you can see layers of the star go above this photosphere, and this photosphere is getting bigger and bigger. And so we have this photosphere emits sort of a smooth black body spectrum, which is a good approximation. And so the star itself, the exploded star, the synthesized elements, but also the star how it was before, can be sort of observed and imprints these features. Like this is silicon, this is sulfur. So we can actually see how a star is taken apart and in theory put it back together. And this is a dream I've had for 10 years. I have not successfully done this yet, but one has to have dreams. So you can sort of see how it moves and how the spectrum encodes a lot of information. A lot of information is put in by these layers being above the photosphere. And at some stage the photosphere disappears, and you can see in the innards of the explosion. You can see in the hearth of the fire. So essentially what we want to do is we want to take spectrum at a couple of different days. You can do this for neutron star mergers. You can also do this for white dwarfs exploding, which I care about. And then you can sort of put this back together. And I mean, I already put there's a model and we have data. And so the dream is you sort of have obviously a perfect model, because that's how physics works. We make perfect models. And then you put this in this wonderful Bayesian formula. And if your model is not perfect, sometimes that happens, you have a likelihood. You compare data to model using a certain metric, and you have prior, you know something about the explosion itself, and I'm going to talk a lot about this. So these are two sort of unsolved problems where the likelihood problem of encoding systematics. So David said that's easy, and so I'm going to use his expertise to solve that problem. And I'm today just purely focusing on the radiative Monte Carlo code, how to use this to interpret things. So the code that I'm using is called TARDIS. It's an open source code, and it has a couple of parameters like time since explosion, temperature, radius, and density profile. and certain elemental abundances. And then you can make a spectrum. And so this has been used to sort of model the neutron-star merger. This is, I put this slide in because we had theoretically at an MMA workshop. And so we sort of like, put elements in and they matched the spectra. That just obviously doesn't mean that this is the only model that fits. And I think that sort of preempts the problem that I'm going to discuss, because in the end, we want to have the posterior, not a model that looks nice for the spectra. Okay, but the search space, and I'm going to talk for exploding white dwarfs, but I think we can also apply this to many other different problems, is very vast. So I'm going to do an example case. So for one spectrum, let's say we take 14 parameters, like 12 elements and the radius and the temperature of this inner photosphere, evaluation with the code, which is a code that does a lot of approximations, but is still physically self-consistent, takes 1,000 seconds. And then so building a simple grid like that, what we would have done is sort of like 3 points in each dimension, which is way too low, would take you already 1 million CPU hours for one spectrum. And so that is what I want to do. Like, how can we use machine learning and spectral emulators to do this? And there was lots of talks about emulators already. And I'm going to show like, what we have done and like where we are. And it would be wonderful to get all the feedback from the problems and lessons learned from you guys. So to emphasize this problem, like, obviously we want to take multiple spectra, but to make it simple, we essentially just do one spectrum, and with the 14 parameters. And then we sort of want to do the Monte Carlo rate of transfer, but we want to emulate this because it's way too large. So I have a couple of astrophysicists that work with me, former master's student, as well as a current PhD student. But I also think like, it's always useful to have machine learners, to have an interdisciplinary team, because they know neural networks much better, or like any of these techniques much better than you ever will. But I think it's great if you can work with them rather than sort of dumping the problem on them. So one of the things that I always get is like, why not just show like a machine learning algorithm synthetic spectra and say like, no, these are the spectra that we have, and these are the parameters, and then do exactly the same for observed spectra, where in the prediction phase, essentially you say like, you saw the synthetic spectrum machine, now look at the observed spectra and tell me what the parameters are. Well, the problem is this, that essentially you only get a number out. You get 0.6 iron, like 60% iron, for example. But we want to have a probability density. We want to have like actual uncertainties on these. We don't want to have this. And our code does not simulate all the physics, which is, I think, the problem that we all have. And so I think it's important. And so we don't know what the machine does with the missing physics. We don't know how it interprets it. It will likely interpret it in a way, in an unpredictable way, and will give us answers that are biased, because like, it thinks there's more iron, because like, dust, it interprets the attenuation from dust as more iron, for example. So that's why I like emulators a lot. So essentially what we do is we say like, these are the parameters that we would give TARDIS, and this is the spectra that they produce, and now find a function that goes from these parameters to the spectra. And we heard like, neural networks can be perfect function approximators, so that is the main thing that we sort of tried to do. So once you have an emulator that's trained, and we have been doing this for like, at least in astrophysics, for like 20, 30 years. We have interpolated in stellar spectral grids, which is nothing else but an emulator with simpler methods. But I mean, we've been doing this. Once you do this, you can essentially plug this emulator here into the model, and you can do what my dream was, to evaluate the posterior, if you have a good likelihood. And you have sensible priors, and some other things. So what we do for training and validation is we sample our 14-dimensional parameter space. I shouldn't say only 14-dimensional, because like, I'm going to show one of our applications only has 5 dimensions, and I'm going to show the results of this. What we do most of the time is we use the Latin hypercube to essentially sample the space uniformly. Like generating a sampling space for generating a training set for an emulator is not that easy if you work in X many dimensions. So this is Christian's work, and he's just about to publish a paper on this. So he does an emulator for collapsing massive stars to measure distances in the end. So this is low dimensional, it's 5-6 parameters. And so what we did there is like, generate the grid. We had only 700 spectra there, and then do a PCA decomposition. And you use like 28 PCA components and interpolate using Gaussian processes in the PCA component space, in the PCA coefficient space. Yeah, this is a brief overview of what Gaussian processes are. It also gives you uncertainties, but I'm not going to go into this. And so essentially, that's the process. Like, the TARDIS parameters go into the Gaussian process to interpolate on the PCA space, and then you reconstruct the spectra from the eigenspectra given the components. And this is how it works. We have TARDIS, the blue line. So there's 2 lines here, and you can see this works amazingly well. Like, the lines overlap. Here's a residual, like it has plus minus 5%. And it really, really impressively essentially emulates something, and it takes milliseconds that TARDIS takes 1,000 seconds to calculate. This is not even 1,000 seconds. This is like, multiple hours, because this is more physics that we switch on in the code. So this is then an actual fit of a supernova, and we can see, like, it sort of reproduces many of the features relatively well, but this is also where the likelihood comes in. Our code is not a perfect physical representation of a collapsing star. No code is, and so I think that's something we want to investigate more. How do we compare model and data? So for my interest of looking at exploding white dwarfs, it's a high dimension emulator, 14-dimensional. And currently I have 80,000 spectra. I have the training set online, and everyone can play with this if they want. I'm going to show this later. So I've designed, with the help of some of my colleagues, currently this network. It's a 2-layer network, has sort of 100 neurons each on each layer, and then in the end goes to 500. So this is a 13-dimensional, 14-dimensional input space, and then goes to 500. I use ReLU because everyone seems to use ReLU, and it sort of works. It works relatively well. So this is the worst 1000s. I was not brave enough to show you the worst validation, the thing with the worst validation loss, but I think we're still training the hyperparameters. But I think it gets the features, and it can interpolate with 80,000 spectra. And this is like, the best 1000s. Well, I don't give you the best, but I essentially give you like, the best 1000s spectrum, and you can see it works remarkably well. So once you have this, you can sample the posterior. This is just an example because I was excited, and I plugged it into my little MC sampler and sampled in these 15 dimensions, and we actually get correlations and things like this, which I think is really cool. This is the future once we are sure that the network works. Anyways, this brings me to my summary. So I think emulators are great, and I don't have to tell you this because over the last 2 days I realized everyone is doing this, at least in this conference. I think not out in the real world, but I think that was really nice to see that so many people are trying this, and I think we can learn a lot from each other. You can enable essentially the comparison between high fidelity physical models, which is exactly one of the problems I feel we're having, to the complex data that we're seeing. Gravitational waves, EM radiation, spectra, light curves, and so on. There seems to be different methods that are useful. So the PCA Gaussian process emulator works relatively well for low dimensions and for small training sets, and we need to use neural networks. So there's lots of hyperparameter optimizations left to do, and I wish I could come up here and give the talk and say emulators, I've got it, you just come to me, I tell you. But this is not true. I still am at the beginning, and so my summary includes lots of questions. So, we know that neural networks are potentially universal function approximators, but this is only for a really large number of nodes. I mean, this is a mathematical construct. It's a finite number of neurons, but it's not like 2 or 20. So I have a difficulty finding out like having an understanding of like how many do you need. Does this mean like when your neural network emulator doesn't work, is it because like my network is not good enough, or because simply there's not enough information for it to interpolate? So learning this, I think, is really important. How to infer the uncertainties that come from emulating, I think, is a really important thing, and that's something that I would like to think about. Can we infer the needed size for a training set? Is 100,000 enough? Do I need 1 million, or would 10,000 be good enough? So I know this is also a Shimmer meeting, and so I also want to talk about cyber infrastructure in the remaining 12 seconds that I have. Cyber infrastructure for open source codes like TARDIS. I think I think a lot now that I'm becoming getting a little bit higher in the hierarchy about software sustainability. Like we talked a lot about the codes that we need to do, make the models. And so like one of the things that I think might be really cool is if we get more physics people into helping build these codes. And so I was thinking we're doing Google Summer of Code, and we attract a lot of software engineers, but it's difficult for us to attract really great physicists that work with us on the code for 3 months. And this is something for the discussion panel. Thank you very much. And this is where you can find, or you can email me, this is where you can find the training set and the spectra if you're interested in playing with 80,000 spectra.
Thank you, Ken. Good. Yes, I'd like to let me set up the computer. Next, we have Ashish Mahabal at Caltech. It did work earlier.
Yes.
They put that on.
Thank you.
I'll warn you when you want that.
Okay. Can you also give me an earlier warning? Maybe a 3-minute warning.
Okay, good.
Good morning. I think we still have a few minutes of morning left. So, my name is Ashish Mahabal. I'm at Caltech, the Center for Data-Driven Discovery, and I also lead the machine learning for Zwicky Transient Facility. And what I'm going to do today is talk a little bit about driving towards interpretability of deep learning, especially. Daniel gave a great introduction of what deep learning looks like, and Wolfgang presented some problems that are with that. And my title here, Driving Towards Interpretability, should tell you that we are not there. Right? We are still some distance away from that. And some of the projects that I'm going to talk about, so Kshitij, Nima, and Fabian, and Meet were heavily involved in that, and some of the other projects that are going on, so Dima and Uma, who are in the audience and will be talking later, have been involved in those. So this is more about interpretation, not inference. So what I mean here is that once we get some results from deep learning, how can we figure out why we got those? Why is a difficult question? So why and how, somewhat of a combination of that. So somewhat of a bit of back paddling to see, once we have gotten the results, which elements of the deep learning network may have helped us get there. And optimization comes in quite early, so you have to try out various things when you start on a problem. But even after you have settled on a problem and you're getting good results, it's not always easy to find out why you're getting the specific good results that you're getting. If you're getting bad results, you don't worry about that much. And this especially started happening because we were using a lot of machine learning before, where you were in the domain where what you could do is that extract a lot of features and use those features with machine learning. And it was still a bit of a black art, but it was closer to interpretable. But when we came to deep learning, it became a much blacker box, and things were even more difficult to understand at the time. And that's why it becomes very important that we do understand about that. So for the last couple of years, there has been a 4-year program that's been going on at DARPA, led by David Gunning, and 2 years in now, 2 more years remaining. So you can see that what they say about today and tomorrow. This slide is from 2 years ago. The tomorrow has not arrived yet. We are still roughly at the same location. Some progress has been made, of course. So what one needs to ask is, once you show images of cats and dogs, for instance, when the classifier tells you that it is a cat, why did it say that? You can get a probability, sure, but then which are the elements that came about? And so can you explain about that this is a cat because it has fur, whiskers, claws, and we are getting closer and closer to that. But when you have complex networks about which you know far less than about cats and dogs. It's far more difficult to talk about that, and I'll come to some examples related to that. So again, another slide that emphasizes that the decision trees are on the right where they're very explainable, but on the y-axis where what we want is that prediction accuracy, then it may not be great there, and it's the deep learning where we should be going, and as the arrow indicates, we should really be going in that quadrant, and we are not there yet, far from away. There are great tools available now, like TensorFlow, for instance, where you can set up various their workflows so that you can see how the variables are changing and so on. But even for that, what you need to do is that you need to still ask the right questions where you're looking at that. And that asking the right questions is where the crux of most of these things is. So some of the applications that I'll be talking about are image differencing without subtraction, DMDT, or how we converted time series to images to use the power of CNN, and if I get time, a little bit on RNN and its variants. So with ZTF, what we are finding is we are alerting the world to hundreds of thousands of objects, interesting objects every night. And the variation in these is quite a lot. So for instance, these couple are supernova, and this is a transient which in the reference image had nothing. So in general, what happens when you see an alert of that kind is that the crux is that in the difference image there is one object, if it is a good clean subtraction. And based on that, you are supposed to then be able to say what kind of object it may have come from. So if it's a supernova, there's a galaxy nearby, so it's relatively easy. But when you see something like that, it could be a flaring star, which is what happens in many cases, but there may be very other interesting cases, like when it's following gravitational wave detections. There are all kinds of possibilities there, and those are more interesting because you find lots of those and only one of them is likely to be the counterpart. So that is what one is trying to go after. So traditionally what is done is that one has these reference image that is made, and then the reference image is subtracted from the new science image that you have taken, and in the difference image then you look for your transients. But can one use neural networks to do that in a more straightforward way? Because what we have is that the current techniques also lead to a lot of artifacts, especially because you have to really match the reference image very well with the science image in many, many different ways. The seeing would be different, the depth would be different, and all kinds of other parameters. So we came up with this encoder-decoder network where what one could do is that just give these pair of images, and of course after lots and lots of trainings, and to the encoder and decoder, the network would just tell you that, look, this is the transient that you're looking for. And we succeeded in doing that using lots of simulations and CRTS real data, and that was working really well. So this is an example where you just give this and then it'll come back and tell you about this. And the way it was built is that you've got this image, and then you could either take real images or put these artificial images in there, use different PSFs so that you know that the night when the observations were taken and the night when the reference image were made could be very different, and then you come to these pairs of images, and finally this is the ground truth that you can get to fairly easily. So these training cycles involve different PSFs and all kinds of things, and now what we are doing is that we are moving towards classifying this for ZTF now. So this is how the convolutional neural network, the encoder-decoder works, fully convolutional. And these are some examples of how the science and reference images are, the difference images. This is what the current method gives, and this is the kind of output that one can expect to get when one is there fully with ZTF2. And with ZTF in particular, what we want to do is we want to be able to do it in real time and using the 3K by 3K images that we have, not the 256 by 256 or smaller images that we have used. This network, we had trained it with single transients, but it was very good at finding multiple transients also. You can see that in this image there are at least 4 that are well seen, and there may be slightly fainter. So we come up with a probability with these, for these also. The other thing that happened is that cosmic rays that were in the images, they were rejected automatically because in the training those sharp small things were not there, so it successfully was able to remove that. But what we are now trying to do is try to understand that it is doing the thing that it should be doing properly, because when you give these 2 images and it tells you this is the transient, meaning how do you know that it has dreamt of that transient, right? It could be that all the examples that you had given, there may be some areas where it had seen more transients, and then no matter what you give, it would give you transients. Using blank images, we have made sure that that does not happen, but as we train with different sets of data, we need to be very sure that what's happening. So we go through various different layers of the network and try to visualize them in different ways to ensure things of those nature, for instance. So that was one application that we had. But when you come to time series, it's a completely different ball game. With time series, what you have is that these are very gappy. The gaps are very irregular. The error bars on each of the points are very different, and then still you have to use that with that. And many of the existing methods, especially deep learning methods, the errors get ignored completely. And that is where what we want to be able to do that. So what we decided is that there was a lovely hammer that we had in terms of deep learning, CNN, and our problem was really not a nail, so we decided to convert our problem into a nail. What we did is that we decided to convert our time series into images. Normally, you would convert the time series into a set of abstractions to make them to be the same dimensions. So you have two light curves, one is 50 points, another is 40 points. You cannot directly compare them, but you bring them to 5-dimensional space, and you could do that. That is how it's traditionally done, and this is the workflow. But what we decided is that why not convert the time series into images and simply give it to a convolutional neural network. And the images have a set number of pixels, so you can use them directly that way. So what we did is that this is our typical time series. So take every pair of points there, the delta t in there and the delta magnitude in there goes and fits here where the axis is delta t days and dm is on the y-axis. And these rectangles are very uneven. So you take into account the cadence of your survey that way. Here we were using CRTS data, so they were 10 minutes apart, so we had to make sure that our delta t's here are 10 minutes. But then as you go away, you don't have too much variability in much longer term. That is why these pixels, these rectangles are much larger. But then we map them back into area equalized pixels. So no matter what the size of the rectangle here is, we get the same number of points in. And remember that here, if there are n points, we have roughly n square points here. So we are getting a density there. And so these are really small images. We were going to only 23 by 24. So the dimensionality is really reduced. But the interesting thing that we found there, and this one kind of a diagram that we would get, and we went to a large number of periodic variables that we had with CRTS, very different sets there, very unbalanced set, and we took only 7 classes which had at least 500 examples. 500 is large enough, but not really as much as we would hope, but 500 is what we could go to. So 7 classes, and those 7 classes look like these. And you can see that some of the subclasses of RR Lyrae do look still similar to each other in this scheme also. So our classification when we gave all of these was not great for those classes. But the thing that we are then using is that we are trying to use the cadence of the survey to subtract the background of the cadence, because no matter what object you are observing, if the cadence is fixed, you are going to get some repeated kinds of patterns in that. For instance, that's why when you look for periodicity, you find period of 1 day to be very predominant if you don't take care of that, because you are always observing near the zenith. So this is like having a video where much of the part is static and there are a few people moving about. So each of our classes is, say, like a street, and the vehicles moving on the street are the specifics of the particular object that we are looking at. So we are supposed to be separating out different streets, and on that street, based on the vehicles moving about, try to get to them. So what we had to do here is that we had to fit a pair of things to that. L, which is a low rank matrix, which represents the kind of background, and S is the sparse matrix, which determines the specificity of the particular object or class that you are looking at. And then you have to iteratively fit that simultaneously, so that when you get to that, then you can describe your DMDT image as a combination of B plus CI plus S. So a combination of 2 different backgrounds, one coming from source, one coming from the cadence, and one of the object itself. And once you do that, then the classifications are good. So here, the main thing is that you're not using any domain knowledge except for the binning, and that is an area I may not be able to go into today, but that's worth looking at. And without doing any extracting of features, then the results are comparable to and slightly better than something like random forest. And if something works great with random forest, you know that it's a good thing. And if you can beat that, then sure, you're doing slightly better than that. And if we did a trick, a little bit of cheat, and removed the class background class-wise from before, we get fantastic classifications. So these are the classifications that we get if we have done the class background subtraction, which is, I agree, a cheat. And so that's what we want to do now, is figure out how the class background can be determined, so that we don't have to do it per class, but we can do it simultaneously for the cadence of the survey and the classes together. And then one other thing that we found is that in class A, the first class, which was the biggest one, it had more than 50% of examples, we found that there were 2 subclasses. The network told us about that. So now we're going into that and trying to figure out which objects belong to each of those. So these are likely to be contact binaries and semi-contact binaries, for instance. Perfect. And so we have been applying this to many other things like diagnosing the lock loss with LIGO. And there are many channels that LIGO has, many external features that one can look at. And this method applies perfectly well to that. This is an earthquake, for instance. And if you look at the DMDT when there was an earthquake, you see that it's completely different from when there was a quiet zone. And of course, this is big. It's easy to see that. But how can one look at it when the perturbations are much smaller? So that's where we're driving towards. And what we have been using is that we used many cavity channels in order to do that. And this is what we get with random forest, and this is with CNN with DMDT. Again, the improvement is great over random forest without going through any features that random forest would use. Now, so for the interpretability of many of these things, we've been hearing of GANs, and these are fantastic. The things here, for instance, we know what they are, but you tweak them a little bit, and suddenly, though to you the images look the same, they are called something completely different by the network. And then there are these deep dreams that Google AI-based data came out, because there were so many dogs in the original data set that if you tweak not the weights, but tweak the original images, then you can see that how many puppies there are in the images. And that's not what we want to be, because if we have our output that is similar, we want to be able to figure out how the weight should be changed and how to interpret that rather than what the input should have been. And so the same has been used for style transfer, and some of those things we cannot directly use in our thing, because again, here what is happening is that though these are images, there is a certain midrib, and so there is a special section. So unlike dogs appearing anywhere, our features are not appearing anywhere. There is a certain symmetry to them, and we need to figure out what we can interpret based on that. So we've been looking at various things about interpretability using various standard things like activation, maximization, saliency maps, and class activation maps, which looks at different parts of the thing and trying to understand all the different things based on that. And there were some very interesting conclusions that we saw, not conclusions really, early work, because we are still trying to figure that out. Because in case of these eclipsing binaries, the attention was more to what was not present. So in areas which were mostly dark, we found that that is where the network was paying more attention to. And so that may be because it's the age of what we are seeing where there may be a lot of detail. Or in case of some RRBs where the period is typically 1 day, it was paying a lot of attention to very long periods. And that's something that we need to go into more detail to figure out about. And then I just wanted to tell you about ZTF. There are 1 billion time series out there. Please take a look at it, DR1. I wanted to go a little bit into RNNs, but the main thing there is that we may want to ignore some delta T's that we take there to improve our classification. So that is, again, some interpretability that we're getting towards, and less may be more, because there may be areas of your time series where you are not really adding information, and you may want to curtail some of those time series to get the best results. And there are many other things that we are doing. So Dima will be talking about a couple of things later, and we have been doing some, again, obvious applications of these to remove artifacts of all different kinds. And I will leave you with this code that Jan LeCun quoted a couple of years back, which Denker had made in '87, that when a network is given more resources than the minimum needed to solve a given task, the symmetric low-order local solutions that humans seem to prefer are not the ones that the network chooses from the vast number of solutions available. Indeed, the generalized delta method and similar learning procedures do not usually hold the human solution stable against perturbations. What are the lessons that we have from that? So we have been throwing a lot of computation and we get results, but are those the best results? Can we reduce the sizes of the networks to get things be done better? So that's the area that where we want to keep driving. And many times it's not the destination that is the fun, but it's the journey, because once everything is explained, then we just have to sit back and do nothing, right? That's not the best time we need to get to. Thank you.
Okay, next we have Daniela Huppenkothen from the University of Washington, the Dirac Center.
Thank you. So I want to talk a little bit more generally about astrophysical inference in the time, can you all hear me? Okay, good. In the time of sort of machine learning. I want to start this out with a quote from a recent paper. So I'm an astronomer by training, but I hang out a lot with statisticians. And the field of statistics is currently engaged in a bit of soul searching with respect to what data science is and how it relates to statistics. And so there was a recent paper in Chance magazine that started out with a quote, and I want to take you back to the early 20th century. And it said, the founders of modern statistics proclaimed that statistics could only be applied to make causal inferences when using data from randomized experiments, but not when using non-experimental and observational data. And that's kind of sad because we never have we never have randomized experiments in astronomy, and clearly we've been doing astronomy. So that same paper went on to say, not surprisingly, many scientists ignored the statistician's degree and continue to use observational data, which is fundamentally what we've been doing for the last several thousand years or so. I very much encourage you to check out that paper. It's a really fun read about data science. So, but what I would argue is that in terms of statistics, what we've been doing for the past 100 years or so, up until maybe 20 or 30 years ago, has been fairly straightforward in many ways. And so this is a plot from a paper I did a few years ago. This is a power spectrum, so it's the Fourier transform of a time series, and I fit a bunch of parametric functions to it that have physical meaning. This is from a black hole source, this is a Chandra observation. And in terms of statistics, this is fairly straightforward. You kind of know the sampling distribution of this kind of power spectrum. You know these parametric functions, and you can directly interpret it in terms of whatever physics you care about. And so I think a lot of science has been like this. There's been a lot of clever things that have been done, and there's been a lot of work that went into making that plot, but sort of the structure of the problems have been reasonably straightforward. And that's been sort of changing for a while now, and it's continuing to change with things like the Large Synoptic Survey Telescope, which is scheduled to start fairly soon, which will see something like 40 billion sources and something like 10 million alerts per night. And then the question is, what do you do with all this data? But beyond just like the size of data, I think we've seen a whole bunch of examples where people didn't have very big data sets, but very complicated data sets. And I think that's increasing in the future too. And I want to point to one sentence that François Lanous said yesterday that I think is very important, that as we improve data quality, understanding the data also becomes more difficult. So that then requires different ideas about how we deal with our data. And so the big question is, how do we make sense of all this data? That is basically what inference is. And I think before we start asking, how do we make sense of this data, it makes sense to ask, what do we actually want to learn? What is the fundamental question that we want to ask? And the paper where I earlier pulled the quote from sort of goes on to classify, in terms of data science tasks, sort of three big classes of tasks. And one is pure sort of descriptive tasks. And since this was written by a health scientist, this is all sort of the example taken from there. But the example is sort of, how can women aged 60 to 80 years with a stroke history be partitioned into classes defined by their characteristics? So it's basically just a kind of type of clustering task, for example. Then there are prediction tasks. Given that you have some person with some characteristic, what is the probability of having a stroke next year for women with the certain characteristics? And there's been a lot of problems in astronomy now that's been sort of phrased as this kind of task, and Ashish just showed us, for example, a couple of examples of that. And then there's causal inference in terms of like this particular problem. The question is, will starting a certain treatment reduce on average the risk of stroke in women with certain characteristics? And so there's a cause and effect that you're trying to learn. I would argue two things. I think one, most of the things that we actually care about fall into this causal inference category, because as astronomers, as physicists, what we want to know is we want to learn something about the universe as a whole. The other thing that I want to mention is that this sort of classification into three different types of tasks, I would argue that the boundary between them, they're not separated out by the different types of analysis you do. And indeed, some of the analysis algorithms that you can do come up in more than one of these boxes. I would argue that the difference between us is really the question of what you're trying to learn, what kind of information you're trying to get out of it. And so one thing that you might say is like, well, if we care about causal inference most, one question to ponder is where this distinction breaks down. And I think there were some examples, especially yesterday, where this is true, and that's something I would love to discuss with people. So, but one thing you could say is like, well, if we care about causal inference, clearly we should just, take our Bayesian approach, or your frequentist approach if you prefer, and build a kind of hierarchical model of your world, and you're done. If you're like me and spend significant time in David Hogg's group in New York, you sit down and you start working on a problem, and in the end you realize that you really need to solve all of astronomy before you can solve the problem that you're trying to solve. And so this is an example that David Hogg wrote down where you have you're trying to understand astronomical images, and you realize in order to understand astronomical images, you need a sky model, you need to know about cosmic rays, you need to know about stars, you need to know about star formation, you need to know about galaxies, and you need to know about cosmology. So you need about everything, and clearly that's not going to be possible to actually do that. And so one example basically of what Wolfgang was showing us earlier was to say, well, maybe we can take machine learning, and maybe machine learning can help. And then you might ask, well, if I can build really clever machine learning models, maybe we don't need astronomers anymore. Maybe we just need our neural networks. I would argue that the answer to that question is no. I think we still need astronomers, especially since I'm not in a tenured position. I'm really glad about that. But more generally, I think we need astronomers, especially at two particular points. And the first point you need an astronomer is figuring out these initial questions, how and what. And here's an example that I want to highlight. Recently, there was this photometric challenge where the LSST collaboration put out simulated time series and said, classify this. And the fascinating thing, this was on Kaggle, and that's a big platform for doing these kind of simulations. The person who won this was a graduate student in astronomy from here, from Berkeley. And the interesting thing, you probably can't read this in the back, but when he sort of talked about his solution, he said, I am an astronomer studying supernova cosmology, so my work mainly focused on trying to tell the different supernova types apart. This ended working out well because everything else was fairly easy to tell apart. And so he used a lot of his physical understanding of the world to try and build this model, and that echoes a lot of what we saw yesterday in these physics-informed model. Recently, there's also been a competition for causal inference in the health sciences, and one conclusion of that was very similar, that for sound causal inference, you don't just need adequate data analysis techniques, but also subject matter expertise about the causal structure of the problem in order to do well, and that actually limits the types of competitions you can do. And so that is kind of one place where you need humans. I think the other where you need place you need humans is trying to interpret what your model actually gives you. And that's what I want to talk about. And you might ask why. You can't just do this approach where you pour your data into a big pile of linear algebra and collect answers on the other side. And if it doesn't work, you just keep stirring until they start looking right. But fundamentally, we want to know something about the universe. And so the first reason why you want to interpret your model is trust. And here the problem is that a single metric like classification accuracy is almost always an incomplete description of what you're actually trying to look for. And so here's an example. Here's a recent paper. This is one of the big issues for LSSTs trying to estimate redshifts photometrically. And so here are example. This was a random forest approach to find photometric redshifts. Here are known spectroscopic redshifts. And you can see there's a big spread. And so if you're trying to do science with this, with your neural network or with your random forest, you kind of have to trust that it does the right thing. And ideally, they would all fall on this line, and you won't trust it unless you know what it's doing and why. If it just gives you a number, you don't really know why you should trust that. And so that is a big issue. The other thing is that we are fundamentally interested in learning things, and so finding causal structure is one of the big questions in a lot of our science problems. So thinking about causality is an important issue, why you want to interpret it. Although especially with neural networks, I would caution people that it's easy to misattribute causal structure to things that might not be causal. One thing that is less important for astronomy, but important generally, is safety concerns in terms of, is the thing that I just built safe? Here's an example where people managed to like print out a stop sign with like slight modifications so that a vision system would just completely ignore it. And obviously, if you put that into a self-driving car, that would not be safe. And so this is not important, or this is not something we worry about in astronomy, but I think we should worry about it in terms of teaching machine learning to our students, who might then move on to applications where safety is a concern. And then one of the big ones that I worry about a lot is bias. This is an example from the Galaxy Zoo citizen science project, where they found that people show a significant bias in favor of anti-clockwise direction of galaxy arms, and people weren't really sure why. But clearly this produces a bias. If you then use that training data to train machine learning algorithms, you will get biased results. And so interpretation can help you try to understand where your biases are. Here's a question to ponder for you. Are there training data sets in astronomy that are unbiased ever? I think no, but I would love to chat about this if you're interested. Okay, the last reason why you would want an interpretable model is that you can only really debug or audit a model if you can interpret it in some way. Otherwise, you just have a number that may or may not be right. And so you want to debug and audit it for all the reasons that we talked about earlier, including like fairness or lack of bias, including privacy, including robustness, causality, and trust. And so when are models interpretable? Can we ever build models that are intrinsically interpretable? Yes, one way you can build a model that's interpretable is if you have a model that you can completely understand in your head, where in your head you can put in an input and you can simulate through what the output should be. And some decision trees and some linear models are like that. So here's like a simple decision tree to decide whether to give someone credit or not. And this is a simple enough decision tree that you can just like go ahead and simulate exactly what happens. So you can stick it in your head. The problem is most models aren't like that. Here's a more realistic tree of how people might make these decisions, or how systems might make these decisions. And that, of course, you can't keep in your head anymore in any sort of way. So most of these models, I would argue that many of the classical models we've been working with, where you have sort of the traditional inference procedure, are basically things you can put in your head. But in these cases, you really, really can't anymore. But you might be able to decompose them, and then understand parts of it, understand the relevant parts. Here's a schematic of a logistic regression classifier. And depending on what kind of inputs you put in, this could either be very interpretable or very not interpretable. But even so, you might be able to pick certain inputs out of it and certain weights out of it and try to understand what it does. And then finally, one of the other things is this notion of algorithmic transparency, and that is if you can sort of understand what an algorithm does, even though you don't necessarily can entirely understand what it does at any given sample. So one thing you could do is you could, for a deep neural network, you know that it will often learn sort of lower level representations of certain salient features in your images. One important thing is that humans have no algorithmic transparency whatsoever. Our brains are entirely opaque to this. The other thing you can do is interpret things post hoc. You have your model, you're trying to now interpret it post hoc. One thing you can do is you can build natural language explanations to things, and this is like an example here where they built natural language explanations to classifications in that image. You can visualize this, and Ashish gave us a few good examples of interpreting via visualization. You can learn by example. You can put in examples and learn by that. How much time do I have left?
You have 1 minute.
Okay. One other thing you can do is you can train both a black box model and an interpretable model, and then compare them to one another and try to use your interpretable model to figure out what the black box model is actually doing. And there's a whole bunch of configurations you can do this. And the other thing you can do is you can train a black box model, and then you train an interpretable model on the predictors of that black box model, and then interpret that. And then here's an example. This is a paper by Ribeiro from a few years ago, where they built a machine learning model, and then they built this explainer that basically looks in prediction space sort of close to the prediction that you're interested in, and builds an interpretable model that locally tells you what's happening. You can also build an ensemble of of interpretable models and then compare those and try to learn something through that ensemble, and that might give you a better idea of what's happening. And so when you ask which kind of model is easier to interpret, whether you have some kind of like logistic regression or some deep neural network, I would say the answer is really, it very much depends on how you set up this model. You can build a logistic regression that is super uninterpretable because you put in inputs that are hard to interpret. And so to conclude, match the model to the real world goal of whatever you're trying to do. I would argue to choose the simplest model you can get away with. Critique your model. That should always be an important part of your procedure. There's a really good paper by David Bly about this, which I encourage you to check out. And then share your models openly so others can interpret them as well. Thanks.
Thank you. So we'll bring the speakers back up. We'll do a somewhat abbreviated question period. The mic in the room is now dead, so that means that I think we will have audience members shout out questions, but then try to make sure your answer is such that people who are on the line can understand what question was being asked. Does that make sense? Everyone good with that? So I'm giving you guys the talking stick. You have the talking stick.
So as a machine learning person, when I look at these simple equations for physical phenomena with PDEs that give rise to incredibly complicated behavior that you use a supercomputer to simulate, that doesn't strike me as an interpretable model either. So I was wondering if you could possibly talk a little bit about kind of how you see interpretability and kind of simulation of complex phenomena interacting. Like if a machine learning model had a very simple equation, but the phenomena that it described could be kind of arbitrarily complicated, would you still, is that still something that you would see as interpretable and would make you happy?
That's a good question. So I live mostly in a space where you don't have hugely complex simulations, and that might be very different in cosmology. And especially in cosmology, you do simulations and then you do statistical analysis on your simulations to figure out what your simulation just did. So no, it's not clear that I would think them. I think our physics equations, and people who work on this on the simulation side more than me might argue with us, but I think our physics equations, I think we do have a somewhat better understanding of physics and how things like numerical solvers work than I think we do about how neural networks work. So I also, it's not clear to me that interpretability is like an either-or thing entirely. I would probably think they're slightly more interpretable than a neural network, but that doesn't mean like that will just solve, like replacing your neural network with a physics thing will just solve your problem. But you have thoughts?
I have thoughts on this. I mean, bad question. You hit a nerve. You hit something that physicists have been thinking about. I was at a conference a couple of years ago, and one of the, and I do TARDIS, and like, it is a code where you stick in elements and then something comes out, and I know that like I've tested it for different test problems, but I mean, no, it's not obvious to me like exactly how that works, because otherwise I wouldn't have written a code. Otherwise, like, I could have sort of looked at this and interpret this. And so at a conference, I sort of said, like, I think we should have more and more physically complex models. And someone's, like, one of the postdocs said, like, no, because you will not understand what they do. Like, we have these cosmological simulations that Daniela mentioned, and like, they give you, for a set of input parameters, beautiful simulations of a virtual universe. But it's unclear if we learn more physics with this. And I think the simple answer, I think why Daniela was struggling, is we're not quite sure how to proceed here, I feel. So I mean, you know, we're trying different things. We're trying sort of analytical approaches, as well as, like, you know, these simulations, and compare them to data and try to make falsifiable hypotheses looking at the data. But it's something that you did strike a nerve, I feel, at least with me. I don't know if anyone else wants to comment on that.
I would like to add a little bit that yes, it is an important problem. I would try to break down the problem as much as possible, if it is possible. And if one starts with boundary conditions, for instance, there may be areas where one simplifies the problem only a little bit. And emulators like how you were talking about, or generative networks, those would be the ones to go back and forth to do that. But yes, it is a difficult problem, and we have to inch towards that slowly is all that we can say currently.
Yeah, good. Bringing it to you.
This is a question mostly for Colin. I think this is a very interesting analysis, and of course I think it is the kind of analysis that we're going to need since the opportunity cost is very low. The one thing that surprised me is that you focused for binary neutron stars. I would think that, first of all, given that the P astro for anything sub-threshold that we get on the gravitational waves is pretty low given the rate of events. I would have thought, first of all, from the point of view of the P astro associated with any sub-threshold BBH is going to be higher given the higher rate of events that we have. But most importantly, I think the first science rounds from LIGO left us with, and Virgo, left us with some open questions as to whether there is some sort of high energy emission associated with that. So I was a little bit surprised you didn't pursue this search for binary black holes, where I think the discovery potential is higher, and there are open questions that probably we need to answer at some point.
Sure, definitely. You know, it's a risk-reward calculation. We know that binary neutron stars exist. We know they produce GRBs. So, and we're mostly just targeting these quieter things that are further away. So why not? But yeah, definitely doing the more sort of frontier stuff with also looking for binary black holes is certainly something that you should do, and has been done and should continue to be done.
Well, I'll use my privilege. I'll ask a quick question also of Colin, which is that, you know, if you're going sub-threshold, one of the things that was important is you had to rebuild the GBM. And we're headed into an era where, like, LSST decides what alerts we get. But, you know, if you want to go sub-threshold, you really want to dig into the things that you wouldn't quite detect individually in LSST. What do you think the future of that is, or what are we going to do about that?
Well, and that's actually what I was hoping to get at. Right now, the model from the EM community is we'll tell you, you know, what's out there, and then, you know, go do that. What I'm hoping that would happen instead is that the model or the code that gives you that alert can be made available, or we can share this and that so that we can do something more like what I was suggesting. Because, I mean, and not just us, other people, everybody's going to have their own sort of thing that they're going to want to try out. And it's just not feasible to constantly going to the same people and asking for this. I mean, that's what happened with us. We contacted the Fermi GBM people when we were trying to do this to, you know, get help with doing this, but they were just too busy with especially preparing for O3. And currently, you know, for them to produce things, it seems fairly intensive, at least from the outside looking in. Yeah.
Hi. Can you hear me? Yeah, this is a question for Ashish, and the question is, what guides your decision to choose image-based time sequence classifiers over recurrent type of classifiers? And you know, the Berkeley team that's hosting this meeting a couple of years ago published a very effective autoencoder-based time series classifier.
Right. So that was also a fantastic classifier where they too reduced the dimensionality to the same number of elements per light curve. And we were working simultaneously. So at that time, we were not aware of that work. We have been using RNNs recently, and they are also a great approach. But we thought that CNNs were the ones that were more popular at that time. and it seemed to be an easy approach. And that's one of the main reasons that we did. And those could be combined in some sense, because there are many areas where you cannot really use RNNs easily, because what is used in RNNs are the delta T's individually. And the delta T's may or may not be the best ones, and that is one area where we are experimenting right now. In particular, one may have to take care of the annular gaps that one finds, and one may have to tweak what goes in, or when using with multiple filters, etc. So it is a great approach, but it also needs a little bit of tweaking, and I think combining those two would be a great way of going forward.
Okay. Listening to you guys, I'm struck by the following worry, which is we're coming to a time where we might not be able to save all the data that's collected live, like SKA, for example. So if we're making decisions on the fly about what we save that's algorithmic dependent, or how would you even do subthreshold? Should we be worrying about losing data that we change our mind about?
Who wants to touch that?
I'll try. I mean, we can't do everything, you know. As Duncan always says, perfection's the enemy of the good. So, I mean, we do what we can, I suppose. I wish I had a better answer than that, but.
But what's going to be important is thinking ahead for data that we cannot fully save. So, not exactly tangential, but there is a meeting that's happening at Caltech in August where we are trying to think about space nebulae, trying to put computation way out there beyond the orbit of Moon, even closer to Mars maybe, because we cannot get all the data from space. So for those missions, what is it that you could be doing? So how you can make that computing systems autonomous, not just autonomous, but perhaps also send updated computation to them to get that. So it is in that mode that we may want to start thinking about what is it that we really need. And some parts we may want to save so that we don't want to throw all the data. There should be some parts that we could keep, that if there are improved algorithms that we could use, then those are the ones that could be translated for later use.
So this question for Daniel and maybe a few others in the audience. You pretty much showed that you've got what looks like a superior algorithm to template matching that could work in real time, that could be faster. What does it take to actually get that into production and have that be sort of blessed at the highest level so that it's actually running on live streaming data? And is there a moment where the other ones, because they're so computationally expensive, just aren't used at all, and it's just going to be sort of these advanced inference techniques?
Mm-hmm. So I think the community would not want to replace what they have for a variety of reasons. So the best approach would be to augment the existing pipelines. So say use this as a trigger generator, or get the initial estimates of the parameters to like narrow down the search space for the existing algorithms. So I think this would be the best option going forward, and what it would take is like somebody who's like just really familiar with the existing pipelines to just go and add this somewhere, make like a hierarchical search or something. So just somebody who's like really familiar with PyCBC or somebody, they should just go and do it. And there is like a lot of like inertia against changing the entire approach. I think that's like the main factor why this hasn't been done yet. But yeah, I guess a lot of people, especially like Eliu's group, are trying to push for this. Yeah.
So as somebody who works with PyCBC, I think the biggest hurdle so far has been there's a lot of investment that you have to put in to get these things to work, as you know he has, and it's not clear yet how much the reward will be. I mean, the match filtering algorithms that we have right now work fine, and so the need hasn't, at least from my point of view, the need hasn't really been there to invest the time into doing it. But there are more and more people that are doing this, and at some point I think it'll reach a critical threshold, and it will become more part of the searches. The other thing, though, and I think another reason why people are hesitant about it are, as has been discussed, the interpretability of the results. You know, it's a real concern, like if your black box tells you, oh, this is something cool, this is a gravitational wave, but then you go and look at like a spectrogram and you're like, that doesn't look like what are you talking about? Not being able to understand that is a very big worry. I mean, we spent 15 years really trying to understand our pipelines, so we knew that when we did produce gravitational wave triggers, we could stand behind them.
Well, that is a very serious philosophical note to end our morning on. We are breaking now. When are we going to reconvene? We're reconvening at 1, so I'm sorry we cut into lunch a little bit. Just have your insightful conversations more quickly over lunch. Let's thank the whole panel again. That was really great.